somewhere in there is an island of stable, very heavy elements.
Ooh.
Californium. You slam californium into different other ones.
Yeah, exactly. You're slamming unstable elements into other unstable elements.
If you slam californium into alabamium, you definitely gonna come up with something unstable. God damn, I tell you, I can't believe they came over here like they did.
Is there anything that smells good that will also kill you?
Ooh.
I'm sure.
Or has that gene pool been removed from our species long ago?
Hilarious.
This is StarTalk. Neil deGrasse Tyson, your personal astrophysicist. We're doing cosmic queries today. That means Chuck is in the house. Chuck.
Hey, hey.
All right, you got the queries.
I do, right here.
And where'd they come from?
They come from our people at Patreon.
Nice.
The
Very good.
supporters who give us money, and that is why we like them.
No, we like them because they're curious.
Well, that's right. Yes, that's why we like them.
So today, it's going to be all about chemistry.
Nice.
Ooh.
We love chemistry.
I know a little bit of chemistry, but not enough to do a cosmic queries on it.
And I know enough to listen.
So we combed the landscape for a chemist, and we went to the top shelf.
Yes.
Top shelf. And we found
Yes.
Kate the Chemist.
Yes, the Macallan 30.
That was the 30-year.
The 30-year-old Scotch of chemist, baby. Top shelf.
Top shelf chemist. Kate the Chemist. Welcome back to StarTalk.
Thank you for having me.
Yeah.
I love visiting y'all.
Oh my gosh. And let me get your full last name in here. Does anyone in the world know this? Bieberdorf?
Mm-hmm. Married into that.
Like,
Wow.
Just don't blame me.
That's it. That is so funny. Married into that.
Wow. Okay. So
Is your husband a scientist?
He is a scientist. We
Okay.
met in grad school.
That makes sense. All right.
all right. I think we talked about him on a previous thing. Did you meet at University of Texas?
We did,
See,
yeah.
I remember
Oh
that.
my
Nice,
God,
nice
good for
job.
you. Yeah, I was high.
Okay, is that what that was? Okay. Okay, you are professor for the public understanding of science.
Yes.
We need more of those professorships.
100%.
Yes, I know in England they have several of those.
Yep.
That were funded by, who was it? One of the Microsoft guys.
Well, the one in Oxford is the Simonier one.
Oh yeah.
Something like that?
Simone.
Thank you.
Charles
Yep.
Simone. Yeah,
Yep.
he's a Microsoft billionaire.
Okay,
Yes.
perfect. My understanding is he also used to date Martha Stewart.
Yes, he did. He dated her when he went into space.
Oh,
and had her make the food for everybody on the space
on the
station
space
at
station.
the time.
From prison? See, man?
Stop.
Or
The prison stint was short. And it was after that. So, Kate, so you're also an author, and you're host Seeking a Scientist.
Yes.
Do you find them after you seek them?
I do, yes.
Every time.
I seek one every time, at least one,
At
sometimes
least once,
two.
and it works every time. Very glad to hear that. So you're at Notre Dame.
Yes,
Yes.
just took this job.
Yeah, and it's new.
Yep, September.
Okay, well, welcome.
Thank you,
Yes,
thank
yes.
you.
Not welcome. I meant congratulations.
I'll take it, yes.
Yeah, I was there a few years ago. Gave a public talk.
Yes, they speak very highly about
very
it.
proud institution.
Mm-hmm.
Do you teach classes, but they're special classes?
So I don't teach right now, but in a couple years I'll be teaching science communication courses. So we're going to build a science
excellent.
communication minor and hopefully turn it into a major.
so good.
It's so important right now.
Will this be in collaboration with the communications department?
A little bit. So it's a partnership
journalism
with
department?
Yes, that. So
Journalism.
the arts and letters program. So both of our colleges are going to come together, and so we'll take their expertise in the actual communication, our expertise with science, and kind of blend it together. And I think it's
And
going
we
to be
need
really
it
beautiful.
so badly.
So
because journalism is so
badly.
broken.
Yeah.
And science might be a way to sort of stitch that, a force to help stitch it back together.
Well, you know, I'm not even sure if journalism is as broken as we think. I believe that people have siloed to an extent where they can't accept whatever journalistic point of view is being put forward because they can't think critically. So they just go, what the hell, man? That's not cool what you just said there because, you know, I don't agree with you. And
Right,
then
but
that becomes the whole argument.
We need somebody to fix that.
Right. You know, but I think science is a way of actually bridging the gap.
Yeah.
Because when people learn how science works as a way of thinking, it changes their entire life.
100%.
So if you got the journalism department involved, very good. And so are you teaching scientists to be better communicators or journalists to be better scientists?
Both. That's
Okay.
clutch, right? We have to do both of these.
That's amazing.
So for the
Clutch
scientists,
is a new
right?
word.
Like that.
Excuse me. So, did that word come into being? That is, I thought it was so fetch, but I'm just getting past fetch.
It's important.
No,
It's very
it's so
important.
clutch. I love it. All right.
It's necessary. We have to teach the scientists how to communicate,
Mm-hmm.
right? And that could be a number of different mediums, like podcasts, books, written, right? Journalism.
Right.
But we also,
Because the science degrees don't care about that. We're not trained in talking to the public in any medium.
we're really not.
Right.
We're taught to talk to each other, right?
Yes.
And we're taught to write in passive voice, which
Yes.
I don't know if you've ever read passive voice. It's boring.
Yeah.
It's super boring. So if you're trying to connect with the non-scientist, passive voice is not the answer.
Right. But both are necessary to be able to talk to scientists, but then be able to translate to the lay person is what's really important. And for some reason, I don't know, how can I put it? I don't want to say that it's counter to the way scientists are as people. Like my son is right now studying to become a molecular biologist.
Nice.
Okay.
When did that happen? You didn't tell me that.
Yeah, that's what he decided, and he got a full ride.
He has you as a father, and he wants to be in molecular biology. How'd that happen?
That's why he wants to be in
He
it.
wants to go.
He looked at my life and was like, "Oh no, I
need something to
Yeah,
guarantee
let me tell you
some-
something. Comedy is not the way to go." But I told him, I was like, "Dude, that's great. With your kind of personality, you would make an excellent communicator for that." And he was like, "Yeah, I don't want to do that.
Oh, yeah.
Like, I don't want to
okay.
talk. I don't want to talk to people about it. I just want to do it." And I think a lot of scientists feel that way.
Yeah, I just want to go in the lab.
I just want to do it. I don't want to talk about it.
Yeah, shut up and get back to the lab.
Exactly.
Right. Well, I mean, as scientists, we have three categories. The first thing we do is we ask a question. The middle thing we do is we seek the answer. We do our research. And then the last thing is actually sharing it with the public. But that's where we drop the ball. We really don't do it enough. And it takes a skill. My husband is introverted. He's a great chemist. He's a great software engineer, but he would hate to do what I do. And so it takes a certain personality to get out there and put yourself out there. And you also have to have a thick skin. People will come after you for what you say.
Yeah. So what we are here in my office at the Hayden Planetarium. What brings you to New York?
Oh, I'm here for a spot on the Today Show and a spot on the Show.
So we're just like we just squeezed us in.
Yeah. We are a straight up booty call.
Wait,
You answered.
Whoa!
So if you're on the Today Show, then you don't need you're on a Today Show. But then what do you
Well, I like talking to you. Was that the question? I think
That was kind of the question that
it's different, right? So the Today Show, you're talking to a certain audience. It's the American public, right?
Yes.
And they're usually people who aren't necessarily signing up for a science lesson. They
Oh,
could
that
be in
was
the
so
doctor's
nice of you. You
office.
just called our audience smart.
They are smart. They're science enthusiasts,
Right.
right? Wouldn't you say so?
No. So, very important point. Here, we already know our audience, and it's a science audience. The Today Show, people tune in not expecting science.
100%.
And then you slip that in, and now they can get excited about it.
That's the goal.
Yeah.
That's the goal. So do a little fire, do a little dance, and maybe teach one thing. If I can teach
Okay.
one thing, I consider it a successful segment.
Which host will you be with on the Today Show?
So Al Roker, Craig Melvin, and Dylan Dreyer.
Oh,
That's
cool.
our team.
And they always you got to bring in the weatherman because they
Wow.
know science.
And Al's,
Always.
yeah, Al's great.
Al
He's
can
an
rock.
actual science enthusiast.
Yes, he is.
As is Dylan. They're both meteorologists, so they have
okay.
that science background, and
Right.
it's very fun to do stuff with them because they ask the questions too. They're interested,
Yeah,
and
yeah.
they have that science background, so they want to push it just a little bit,
You got
which
it.
I love. Right? You need the buddy.
So we probably did this the last time you came through because I want to get to the questions fast because
Yeah,
we have a million questions that our audience wants to ask.
And
you.
they all know you.
Yeah, they all know you. So
Hi.
yeah. So just a couple of fast ones here.
Mm-hmm.
When you were a kid, did you like burn holes in the carpet and explode the kitchen? Like
Science, mommy.
what kind of were you like girl nerd where this is I got to do this?
Yes and no. So I was more of an athlete. I was a soccer player, so that was the true love.
All right.
But
Very nice.
I was a very one who asked a lot of questions. So my parents would count the number of questions I would ask in a car ride because it would drive them nuts. My mom was more a helicopter mom, so there was no blowtorch anywhere near me. There's no chance I would have ever been able to set something on fire.
Wow, okay.
But I was able
I
to
could
do
see this in a
stuff.
sitcom.
Yeah.
The over curious kid just, hey, mommy, daddy, how about that? And then the car, and then the next scene, you're just out on the street. The car keeps going. Just leave you.
I'm sure they thought about that. I am positive.
Or more kindly, they drop you at a museum somewhere and then they keep driving on.
Yes, that's perfect. That's
Okay, but
perfect.
so if she's a helicopter mom, what freedoms did you still have to express yourself?
Okay, so this is where I really appreciate what she did when I was younger. So she made one bathroom safe. Like there were no chemicals, like cleaning chemicals, I should say. But there was food coloring, there was shampoo, bath soap, bubble bath.
Stuff that can't kill you.
Stuff that can't kill you. Put it in this. She had this big green plastic bowl, and it was like go to town. I will say the food coloring was removed after the first time.
Okay.
But
Were you
after
green at
that,
the end of that?
I think so.
Food
I don't
coloring doesn't come
remember.
off very easily. Yeah.
Well, if you look at my Instagram, I'll show you. My face was just covered in green food coloring very recently. I had something go wrong.
So I just made that up. You're saying that actually happened?
It happens all the time. I
Yeah.
do this one experiment where I intentionally cover myself in soapy green bubbles, and it comes right off in the shower. Just 2 face washes, you're good.
Okay. All right. I ain't doing that.
I am.
Oh, you
I'm
are.
willing to.
That's why you are Kate the Chemist.
Yes, that's
All
right.
So,
I like it.
So Chuck, give us some of our cosmic curiosity.
Let's get right to it then, shall we? This is Sean Browning, and he says, hello, this is Sean Browning. I'm coming from Hood River, Oregon.
Hood River, yeah.
Why does cesium have such a violent reaction when exposed to oxygen? And what are some of its practical uses that the average person would not know about?
Okay. In the periodic table is kind of shaped like a U. And so cesium is in the bottom left-hand corner. And so the bottom left-hand corner is where your biggest atoms are. And so cesium is really big. And what that means is it has a very, very positively charged core, its nucleus, but its electrons are very far away. So it can barely reach the electrons. And so because it's so big and their charges are so separated, oxygen, which likes to take electrons from a
electron
neighbor.
thief.
It is, exactly,
It
yes.
loves to steal electrons.
It will steal the electrons.
That's a book title, The Electron Thief.
The electron thief.
I like that.
That's your next book, okay?
We'll write together.
All right.
That'll be fun.
Yeah.
But yeah, so it's so big. And so that's oxygen can come in, grab the electrons, and the electrons gladly jump to oxygen because it's much, much smaller and it can reach
Cesium,
its
I'll
shores.
see you later.
Yes.
You don't deserve me. I can do bad out by myself. Oxygen over there been courting me forever. Oxygen, I'm coming, honey.
I can see it.
Yeah. There it is. Okay, so now it reaches for oxygen. What is the result of that chemical reaction? Is it exothermic, endothermic? What?
Probably exothermic would be my guess. It really depends on the situation and
Okay.
where their energy levels are. It will form an ionic salt, and so it either forms cesium oxide or cesium superoxide. So just either 2 cesiums and 1 oxygen, or 2 oxygens and 1 cesium, and it forms these two products, and that in itself is quite stable. The oxides usually are.
Okay, so what does it look? What does this? Because he said violent. What does this violent reaction look like?
So my guess is he's thinking about when you throw these group 1 metals into water. So we've seen this with sodium before, if you've Googled that.
Love me some sodium and water.
Right,
Oh
right.
my gosh. So sodium, you can cut it with a knife. It's a metal, cut it with a knife, toss it in water, it basically blows up.
Yeah,
essentially.
definitely
Yeah,
exothermic.
but that's reacting with water.
It is.
Or is it the dissolved oxygen that it's reacting with?
It's the same process that's
Okay.
happening. It's the electrons being pulled from the group 1 metal.
Got it. All right.
Yeah,
All
and
right.
then it's an exothermic process, like you said, so
Yeah.
that will ignite when you throw it in water. So,
Okay.
But the other part of the questions you asked about, like what are some things that people might not know about
That is-
cesium?
right.
And so the cesium 133, I think, is used for an atomic clock. And so what happens is you basically disturb these atoms. They give off a frequency, and you can use that frequency to measure time.
And how are you exciting the atoms?
It's a disturbance, so usually it's like a push. You want to get it to vibrate, and so
Right.
you just have to move it a little bit, and that frequency is then mapped out to keep track of time, and it's so.
So is it so consistent
Steady.
that
Yes,
you
consistent.
can easily use it? You can set a clock by it.
Nice. Exactly.
In fact, the duration of the second is defined by how many cycles of the cesium atom.
Okay, so how many vibrations do you get in a second with cesium?
It's like 9 decimal places. I'm sorry.
Oh, so it's that's why it's an atomic clock.
And that's why it's very precise.
Right, because if you got 9 decimal places in 1 second, that's pretty damn
we
accurate.
got you, yes.
Yeah, well, you're good for all time.
but
no pun intended. What? Chuck, stop it.
he's on a roll. He's on a roll. You want to know how precise this is?
Right.
For that vibration?
For the vibration
That
in
Kate
1
the
second.
Chemist told us about? It is 9,192,631,770 cycles of that vibration.
So that vibration
is the exact definition of a second.
Of a second.
Yes.
There you go.
Yes.
That's cool.
Right.
And if I can add to that,
Please.
if I may, until that was defined with that precision, the second was a predefined fraction of the year 1900.
Okay.
And so that involved Earth's rotation around
right,
the thing.
right.
The rotation of the Earth was built into the definition of the second. Why wouldn't it be?
Right.
Because there's 60
Since we
seconds.
use that as
60 seconds in a minute,
to
60
make up the
minutes in an hour,
24-hour
24 hours.
clock.
Okay, why wouldn't it be?
Right. Why wouldn't
But
it?
that meant if Earth were slowing down or speeding up,
Right.
there'd be no way to know that.
Exactly.
Because the mechanism that's giving you the second is changing.
Right.
So you offload it onto your cesium atom. Now we say, yo, Earth.
What?
What? And so since
We don't need you, Earth.
we totally don't
We
need
don't
you.
need
Not
you.
only that, you're acting up.
Right.
So since
Plus, you're slowing down anyway.
since 1972, we've had to add 7 leap seconds.
Right.
Just to account for Earth slowing down. And it's all because of your cesium atom.
And that,
Isn't
look
that
at
neat?
that.
My cesium.
I love it. I love it.
I don't know any other uses, though. Is there?
Not real. I mean, I'm sure there's other ones.
I mean, let's be honest. That's enough.
What more could you ask
Come
for
on,
an
guys.
element?
I mean, seriously. Like, measuring time down to a billionth
Yes,
of a
a
second.
billionth
of a
second.
Come on.
That's pretty neat.
pretty damn good.
Yeah.
All right. Hey, StarTalk fans. I don't know if you know this, but the audio version of the podcast actually posts a week in advance of the video version. And you can get that in Spotify and Apple Podcast and most other podcast outlets that are out there. Multiple ways to ingest all that is cosmic on StarTalk.
Will from Euclid, Ohio here.
Euclid?
Euclid.
There's a town called Euclid?
There's a Euclid, Ohio. I've never heard of it until just now, but guess what? I'm glad to know that it's there.
Wow.
Yeah. He says, most gracious thanks for using my question. You probably had this question a bazillion times, but I've never heard an answer to it. So here it is. We've all heard by now that the Mentos and Diet Coke thing, okay, cool. 1, what's the history and who thought of that? And 2, what causes the chemical reaction that everybody puts on YouTube to make the video?
Yes.
The soda geyser. Okay, so that went back to about 1910. It was originally done with those wintergreen lifesavers.
I was about to say, we didn't have Mentos in 1910.
We didn't. No, we
Yeah.
didn't. So it was originally done with the winter green lifesavers. and it
Winto
was-
green.
Winto
Yes,
green.
I remember that.
Yes,
apostrophe green.
Wow.
It's
Lifesavers are that old?
They are. Yeah, they are. And so they go into the soda, like a soda pop, right?
Right.
And so it had that little hole in the center. And so it would make this really neat geyser and it would come out. But then
through the hole in the middle of the lifesaver. Uh-huh.
Yep. But then in the 1990s, the Lifesaver company changed the size of the Lifesaver. The science teachers were upset and they said, all right, throw this experiment to the students. Let's figure out how to replicate this now that the Lifesaver doesn't fit in there. They did a
These are
science.
some committed chemists right
It's
here.
I tell
awesome,
ya.
though. I can totally see high school teachers just grabbing their students
Wow.
and grabbing all the candy, all the soda, and say, all right, figure out what
Experiment.
is it. Experiment. Exactly.
So what's special about the surface of a Mentos? Because it doesn't have a hole in it, right? And if I remember correctly, they're solid candies, right?
It's solid candy, but it has these nucleation sites, so these like little divots, and they attract
On the surface.
On the surface,
Uh-huh.
and so it attracts the carbon dioxide in the soda. The carbon dioxide slams into each other, builds up pressure, and it just shoots out the top.
Wow.
And then they found that Diet Coke has the best reaction because it has the highest carbonation.
There
Okay,
you
I
go.
thought, however,
Yeah.
that's not why they use Diet Coke.
Oh, please tell me then if it's otherwise.
Okay, I didn't think that was why.
There's one part is that it doesn't have the sugar.
That's why-
and so it's not as big of a mess for
But
parents.
it's a mess.
Yeah.
Right, Diet Coke, you just hose up.
Mm-hmm.
But sugar, then the Coke evaporates and everything is gummed up. I thought that was the main reason.
It is one of the main reasons, but
Okay.
if you are on a flight, I don't know if you fly commercial still, but if you are on a flight,
What do you think? Excuse me. I want the subway to get here.
Okay, perfect.
Don't
So
ask me if
I
I
don't
ride
know.
commercial.
You're fancy. I don't know what your world is like.
Ride commercial. Okay.
For the rest of us, when we have a flight attendant go down in a plane, watch them. When somebody orders Diet Coke, just watch how they pour it. It takes way longer for all that carbonation to sink and for them to top it off.
Okay.
So you can actually watch it happen right on a plane ride.
Compared to a non-diet.
Like a Mountain Dew or a Coke or anything. It just has
Anything
that
with a
more
bunch
Do
of
that
sugar in it.
carbonation.
experiment.
Please
and
do.
find that.
You'll see it.
Yeah,
You'll see
plus,
it.
at the lower pressure in a plane, there's less to press down on the CO2 anyway.
Also true.
So that there's more bubbling action
Very good.
regardless.
Yeah, that's a good point.
I will check that out. Okay.
Please do. Please do.
All right. So that means if I have a soda maker machine, a carbonator, whatever those machines are called, because I do own one, but there are 3 settings. There's low, medium, and high.
Yes, there
if I
is.
go to high and then repeat that 3 times, that's the liquid you want for
Probably.
your experiment.
You're also
Probably.
going to blow apart your kitchen. You just made a bomb.
Thank you for saying that.
Next, Chuck.
Andy here from Thousand Oaks. I've heard the human nose is an incredible chemical sensor that not only detects very faint traces of a molecule, but also tens of thousands of types of molecules. My question is, do you use this fact in the science of chemistry to aid in your work in any way, or do you generally avoid smelling experiments due to unknown noxious effects?
I love that. Remind me, because chemistry for me was a long time ago. Yes. You don't actually stick your nostril on top of the test tube.
100%
Right.
accurate,
But there
yeah.
is this
Wafting.
There's
You
this
remember.
thing. So that can dilute it
Yes.
to a level that you can know whether you should get closer.
Exactly.
Wow.
Yes.
All right.
So the rule number 1 is do not eat anything or smell anything or drink anything in lab. Rule number 2 is, okay, we know you're going to smell it, so let me teach you how to do it safely.
Is that
And so,
this?
Yep, it's wafting.
This?
You're
Yeah.
pushing the molecules towards you. If
Some
you,
of the molecules.
Yeah, it's true.
Right.
A small portion of them. But I think part of the question is asking, like, do you ever do this? And do you ever use your nose? I did something just recently where I had to do this, where people helped me by bringing 2 beakers out to my performance stage, basically my stage table, and they weren't labeled. One had water, one had vinegar, and I immediately just stuck my nose right in there because we can tell the difference between it, and then I was able to do the experiment without any doubt or anything. But you use it. You use your nose to protect yourself. It's a way for us to know whether or not chicken is bad or good or anything like that. So it is a tool that you can use if you're safe about it in the chemistry lab.
Is there anything that smells good that will also kill you?
Ooh.
I'm sure.
Or has that gene pool been removed from our species long ago?
Hilarious.
I
No, right? That's
so
a fair
funny.
question.
It is a
Yes.
fair question.
Right?
Yeah, I am sure there is something that smells good that will kill us. I can't think of anything off the top of my head right now. Do you have one in mind?
No, but I have the
Okay.
opposite, which is we know that hydrogen sulfide, is especially deadly at some level well below the level that we can detect it. So when you smell it, you say, this is nasty, I'm going to go in the opposite direction. It was still far from killing you. But anyone but you know what hydrogen sulfide is like rotten eggs?
Yeah, it's a fart.
Fart, okay.
Yeah.
I was going to say rotten eggs, but fine. Okay.
Everybody knows
Go
it's a
there.
fart.
You're a comedian. You can do a fart joke.
Listen, that's the first time I got in trouble in
elementary
chemistry
school.
Yeah.
Wait.
Right. We had hydrogen sulfide, and I took it and put it in an eyedropper and went around and putting it on people so they would smell like farts.
You did that?
not.
I did. Yes, I did. And I got it.
And the teacher said, you should be a comedian.
Of trouble for
Did
it.
you really?
I did. Yes.
You should be a comedian.
Yes.
That's what they
And
said.
I wouldn't have gotten in trouble for it if I had just kept it to the doggone students, but I had to get aggressive.
So
anyway.
yeah, so there's a suspicion in our evolutionary past that there's an idea that hydrogen sulfide can build up in the bottom of the ocean. If the ocean oxygen cycle stops, then you have anaerobic life forms.
Okay.
And hydrogen sulfide is one of the byproducts of them. And if it builds up to a big enough bubble, it'll come up. And if you're on the shore when that happened, and you liked the smell of farts, you would go to it and just die.
Yeah.
And if you sort of didn't care, you died. If you didn't like it, you went to the hills. And so the argument is this happened with some frequency in the history of our species.
Interesting.
That it was built into us.
That's interesting.
Yeah.
I hadn't heard that before. That's
Yeah.
interesting.
Yeah. So all the uncles that said pull my finger ended up dead.
that somehow we still do that.
We're still somehow still there.
Evolution.
Yeah.
It's never the aunt that does it, it's just the uncle. So it's the guy gene that carried it forward. All right.
All right.
Give me some more.
This is John. He says, hello, Dr. Tyson, Dr. Kate, Lord Nice. John here from Arkansas. I used to teach high school chemistry, but I still
Teacher in the
struggle.
house.
All right. Teacher applause. But I still struggle with electron configurations, especially in the transition metals. What is it about that section of the periodic table that makes it so doggone convoluted?
Yeah, and why are they called transition metals? Because the edges, they're pretty clean. We can understand them. You got the gases, the noble gases, and you got the, and you go into the middle, and their representation on the table is different.
Yes.
Right?
Yes.
And you have these others that are a series, then they pull those out. What's up with that?
What's up with that? So one of
Can
the
you
reasons
make that cleaner for the rest of us so we can learn it?
I can try. So one of the reasons why transition metals are called transition metals is because they go through different color changes. And so you can actually see them transition through their oxidation states. And so maybe they're a +2 or a +3.
You can see the color change across the table. Okay.
Yeah, so you could just sit there and watch your reaction go from, I'll just make up some colors, so some blue to green to red, and you're watching it go through different oxidation states. And so you can actually monitor it. So inorganic chemists, which is what I do, we usually like color changes. And that's one of the reasons why we're drawn to that field, is because we work with transition metals. In high school, and also what I taught, which is general chemistry, so the first year of college chemistry, we do general trends. And so we say if something is like this, it'll operate like this. We just try to identify trends. And so the S block and the P block, so the outside areas of the periodic table, they really follow these trends. But the middle, the D block, the transition metals, don't really follow the
You
trends.
sound like prison. Are you in D block? What are you getting now? Okay.
And so that's what's hard about teaching it, especially in high school, because there are no typical trends you can go by.
Gotcha. No
And
general rules.
So there are general trends that you can go by. And there's certain ones that always break rules, like your jewelry metals. So copper, silver, and gold will always... I'm going to nerd out on you, but they're usually D9, but because of the way the electrons fall, they go to D10. And so they can just redistribute their electrons.
I cannot get as excited about
Makes
that.
it more stable.
Yeah.
I'm sorry.
But it's an explanation of why
sounds
we
like a
use
boy
these
band
metals,
battle.
right? Oh, it does.
I used to be in D9, but now I'm in D10. Yeah.
Oh, it's the inorganic flaring. We talk about our d orbitals and where our electrons are, and so I just love that part. And it's just where your electrons sitting, they move around to be stable. If you have, let's say you have 5 orbitals, there's 5 d orbitals. If you have 2 electrons in each
we all
one,
knew that. 5D orbitals.
you all knew it. You all knew it?
We totally knew that.
If you have 2 electrons in each one, that provides stability. But if you have 2, 2, 2, 2, and then 1, it's less stable. And so what it does is it takes another electron and move it over here to provide stability. And so these specific atoms like copper and silver and gold will do that just naturally. And that's why it can be confusing for high school students, because you don't usually teach these exceptions.
And for grown-ups.
And for grown-ups, yeah, for everybody, true. But he's a high school teacher, so just wanted to pull it back, yeah.
Okay, cool. Because in astrophysics, 9 out of 10 atoms in the universe is hydrogen.
Yeah.
And there's nothing easier than the hydrogen energy levels.
Right.
And we don't even have to think about orbitals. There's just a layer. There's just levels. And the electron moves back and forth. But when you have all of these electron clouds, it gets way more
really complicated.
Realistically described, but complicated. Yeah.
It's really hard because you have to figure out how the orbitals are actually going to overlap. Are they going to be complementary?
Right.
Will it be bonding, non-binding, anti-bonding? There's all these different categories.
There are molecules in space, and we have to, but then they're sort of astrochemists at that level.
Right.
I can do most of my astrophysics completely ignoring that. It turns out.
Well, that's kind of interesting.
Yeah, not to say that.
Yeah,
You make me cry.
No.
I have to leave right now.
That was not meant as yeah. Okay, Chuck, what else you have?
All right, this is Mihir Date, I think. Mihir says this. Hey, Kate, Neil, Chuck, there are books on complex topics like quantum physics for babies. How effective do you think these books are? Should graduate level science topics be introduced formally at the elementary level in an engaging and understandable way? The cool experiments seen in school provide momentary excitement, but they don't leave a lasting impact. Books, however, might. By high school age, the kids' ship has already sailed. Grab their attention while you can, I say.
So wait, tell us about your books first.
Okay, I have 7 children's books. 5 of them are about little Kate the Chemist. She's 10 years old, run around their neighborhood and uses science.
Was this a shill?
No.
Was this a plant?
No, I didn't. But I do.
That's her mother. Her mother put that in. Mom, thanks, Mom.
Is that Teresa?
Yeah.
So go ahead.
I have five fiction books. I have 2 nonfiction books, and I have one for adults. It's called It's Elemental. So I just write to try to share science with the general public and try to make it fun.
So are the kids' books doing what you want them to do?
Yeah, definitely. Because the 2 nonfiction books each have 25 experiments that you can do at home with materials you probably already have in your craft drawer. And so what I want them to do is for parents to pick up that book and use it over spring break and do science experiments with their kids.
Okay.
That's cool.
That works.
That's what
I love
want.
that.
Okay, so, and it seems to me, yes, I think an experiment can be lasting. Contrary to the claim of the question, an experiment, yes, it comes and goes,
Right.
but it can trigger curiosity.
Yes.
That whether or not you fully understood the chemical reactions that made it happen, you just don't forget it.
Right.
And so I think educators overvalue the lesson plan relative to the inspiration.
I think so too. And research actually supports what you're saying too, but it also is that you can have a connection with the scientists. So if you show up one time and do an explosion, okay, fine. Maybe you'll spark the interest. But if you keep going back and you form a connection with the students and you form that bond, that's when you can actually make a difference.
Okay.
And so showing up really does have value.
Good. Yes.
But can I push back on the quantum physics for babies,
You
please?
said quantum physics for babies.
There's another one. There's
How effective do you think
there's
these books are?
astrophysics for babies.
That's right.
Yeah.
But
there's a series of these books.
But what do they mean by babies? They're not talking about actual babies.
They're board books that you can flip through,
Okay.
and so they're really small. But I think those are primarily for the parents who can't read another book about the cow goes moo.
Right.
And so it's intellectually stimulating for the parents. They can be better parents.
Mm-hmm.
But at the end of the day, exposing kids to all this vocabulary is just good. So that when they get to the science class, they've been exposed. They're not hearing the word molecule for the first time.
Right.
They already have a general understanding of what it is. Maybe.
Hunter here from Columbus, Georgia. We saw Neil a few weeks ago.
I was just there. Gave a public talk in
Okay.
Columbus, Georgia.
I wanted to ask Kate a question about the periodic table. If the island of stability is real, what kind of properties do you think we might be able to expect from atoms in it?
Ooh.
Okay,
So were you talking about the island of stability, Neil? Or they just wanted to point out that they saw you a couple weeks ago?
Yeah.
Yeah.
Okay.
So this is something that I think is really interesting because as a chemist, I'm familiar with the band of stability, but the island of stability is a little bit outside of my reach. So can I do band and then I throw to you for island? Will
Sure,
that work?
unless they're the same thing and we just call them something different.
It could be.
Yeah,
It
what's your
could be.
band of stability?
So the band of stability basically...
Which is another boy band name. We're the
The band of stability. Actually, that would be Coldplay.
Okay, all right.
Okay.
Kate got it.
So
All right.
the band of stability is all about figuring out what ratio of neutrons to protons makes an atom most stable. And so if you have 20 protons or fewer, the ratio is 1-to-1. If you have more than 20 protons, that number alters a little bit. And so for chemistry, specifically atoms, you have 1.5 neutrons to every 1 proton. That gives you your most stable atom. So that's how I think about it. Where does the island of stability come in? Is that an extension?
Oh, yeah.
at
So,
the end?
okay. So I can only tell you how I have come to learn it, and we can maybe dovetail with what you described. Above a certain atomic number, the nucleus is so large, and every one of them are unstable. You can ask, well, what makes a stable element? Is it stable forever, or just for a few years, or a few minutes, right? So there might be some practical definition of what we call stable, but for our purposes, all those big atoms do not live for long. And the ones we're discovering, 101, 102, 103, which is the limit of the table when I was in school. And 103 was Lawrencium, I think it was, or still is.
Still is.
Still is, thank you. It turns out that the calculations for the stability of the nucleus, when you go beyond the ones we're currently discovering into the 120s, 130s, somewhere in there, and I forgot the exact range, somewhere in there is an island of stable, very heavy elements.
Ooh.
And so you have to get past the unstable ones. Typically, you make another element by cramming protons and or neutrons into a pre-existing...
Californium. You slam californium into a different other one.
Yeah, exactly. You're slamming unstable elements into other unstable elements. See if another unstable element shows up. And some of them live for thousandths of a second.
So if you slam californium into alabamium, you definitely gonna come up with something unstable. God damn, I tell you, I can't believe they came over here like they did.
Alabamium.
Oh, you got me with that one.
Yeah, that's
funny.
But liberals, I tell you.
It'll be the color purple, though.
Nice.
See, that's how you get out
Way
of
to bring
that.
it around,
Wait,
yeah.
so this has been described in physics as an island of stability, which we are all just, our appetite is whetted for it. Because if you have a new element that is stable, what are you going to do with it? What properties does it have? And that all happens on the chemical side, not the physics side.
Yeah.
Right.
So with the island of stability, then, are we saying that it's, because I know like organicium or whatever lasts for less than a second, right?
Yes.
So are we saying
So
these...
organicium, so that's the 118,
118, that's the highest one we know about right
the
now.
highest, the highest
biggest one.
numbered one, yeah.
So I guess what I'm curious about is then, would these atoms then stay around for, are we talking seconds? Are we talking years? Like, what do we think?
My understanding is that they're permanently stable. But what it would mean is your rules either have a new manifestation in those heavier nuclei, or somehow that rule shows up again.
Okay.
But I can't wait till we get there.
Right. I'm really intrigued by that because I'm curious if it's just like relative stability where it lasts maybe a second still, or
instead of a thousandth of a second. Right. Yeah, you couldn't still have a wad of it in your hand.
That's what I'm curious about.
Right. As am I.
Yeah.
As am I. Have you ever wanted one of your questions on the universe answered? We all have questions about the universe. From black holes to quasars, quantum entanglement, wormholes. There is no end to the depths of cosmic curiosity. Well, the entry level of Patreon membership with StarTalk gets you just that. I think it starts at $5 a month. You have access to the question line that reaches our Cosmic Query programming. And not only that, we produce a special Cosmic Queries installment just for Patreon members.
If you weren't the director of the Hayden Planetarium, what do you think you would be doing?
Okay, but this had to be another universe. It wouldn't happen in this universe.
Okay.
I'd be a songwriter for Broadway musicals.
Ooh!
So that's the entry level, and the perks ascend from there. There's a level, in fact, where we send you an autographed copy of one of my latest books. Right now, it's Starry Messenger, Cosmic Perspectives on Civilization. And it's signed with my fancy fountain pen with purple ink. So I invite you to just check the link below. And all of that money goes to our ability to experiment with new ways of bringing the universe down to Earth. So thank you for those who have already joined. And we welcome others to participate in this grand adventure of what it is to bring the universe down to Earth. As always, keep looking up.
This is Jessica. Hello, Dr. Tyson, Lord Nice, and Dr. Kate. This is Jess from Toronto and Dubai. Well, la-di-da, Jessica. Anyway.
Let the people show off where they've been. let them get
listen, you got it. I haven't been to Dubai, so I'm going to give it to you.
All right.
I'm probably the only person here who hasn't been to Dubai.
I haven't been to Dubai.
Oh, okay.
Okay, I've been several times.
Well, we knew that.
For there.
Well, la-di-da. So, in space, where there's no oxygen and gravity is minimal, how do chemical reactions, especially combustion, change at the atomic level? Could studying these reactions in a vacuum reveal new insights into quantum effects, like wave function behavior in molecule bonding or energy transfer? And quantum mechanics says everything is probabilistic. Is there a tiny chance my candle would light just to mess with me? Thank you, Neil, and I love you. And by the way, that's the different kind of probabilistic, so go ahead.
So we should separate that into two areas. There's what are you doing with no air,
Yep.
Right.
but you have two molecules that might perhaps know about each other's existence quantum mechanically,
Right.
through entanglement. Maybe that was a little bit in there. And the other one is just in 0G.
Right.
And 0G combustion is fun. Tell us about that.
Well, what's interesting about in 0G is that all of our reactions behave like gas phase reactions because we don't have gravity, right? And so we get to kind of do stuff that we couldn't do on Earth. We can do it up in space because you can move things around. They expand more. Like a pencil would never float around here on Earth. It would stay at the bottom of a beaker, right? Same thing. Whereas if you're trying to do that
pencils
reaction,
in beakers?
well, I'm just trying to give a solid because if I give just a random molecule, people might not know. But you can visualize a pencil in a beaker, right?
Pencil molecule.
A pencil molecule, yes. It's staying at the bottom of a beaker. We know where it's going to sit. It's going to be at the bottom. It will have interactions.
The whole time?
Yeah, the whole time. But when we go to space, now it moves around. So we have solids that essentially get to behave like a gas. And so the chemistry is just different. And you get to look at it. My question is, do we have combustion reactions outside of Earth and outside of the International Space Station? I mean, do we have to have oxygen to have combustion?
Yeah. So I guess what I was really referring to, which was accurately portrayed in the movie Gravity, okay, there was a small fire that began, and they just let it go, and it extinguished itself. Because normally, on Earth, where there's 1G, the heated gas rises,
Right.
bringing fresh oxygen in to continue the combustion. But here, it ate up the oxygen, no more oxygen in town. And the CO2, whatever the byproducts, can't feed the flame, and it snuffed it out.
Wow.
So you can't burn a candle in 0G, is the point. Unless you have a gentle breeze.
Right. You have to have something moving more oxygen molecules that way.
Into it.
That's so cool.
Right. So that means...
I did not know that.
So you didn't know that?
I love that.
Okay, let's which way?
That is so... You cannot be romantic in space.
So anything that combusts, it assumes that it's just moving through the material to burn the whole thing, right? A piece of paper burns the whole thing, and we take it for granted. It's relying on hotter gases being less dense and rising.
Yeah.
Right. So do you ever try to think about those experiments?
I have not really thought about it because all of my chemistry happens on Earth, and I'm terrified of leaving Earth, and so that's usually where I stop.
I just love that sense. Chemistry I do is on Earth. Okay. No, but if we needed you for space to consult,
I'd say call someone else. It's not happening.
There you go.
I don't do that. That scares me.
You wouldn't go to space?
No. I don't know why that's my line. It just scares me. I don't want to. I don't want to be strapped.
You're flying in a plane. You're like halfway
you're strapped
there.
to a rocket. I don't know.
No, but in plane you still have 1G.
Right.
Yeah.
Okay. All right.
What I think about, though, is how you could do different experiments in space. Like you can do the experiments of a womb because you can kind of replicate that and how the baby moves around with not zero gravity, but they have that vibe, right? They're able to float around. So you can do those type of experiments in space. That's what I think about.
Right. Okay. And so there's some reactions. What's a reaction that could only happen in 0G?
I'm curious. Well, not only, but there's certain ways you could do it. Because I could think about taking two different solutions and have the drops come and collide with each other that you wouldn't be able to do on Earth.
And create these mini reactions right there as they're floating.
Yeah.
That's amazing.
And just have that unfold right in front of you.
So solid rockets, could you do it inside? Like what's in the solid rockets, Neil?
It's solid fuel.
No, it isn't.
Yes, it is.
It's a combination of...
No. The solid rocket boosters?
Yes.
You can go in there and bang on the fuel. It's solid. That's why it's called solid rocket.
That's why they're called solid rockets.
But generally there's another tank that can be...
That's what I'm talking about. That.
Oh, okay. That tank. That has hydrogen and oxygen.
Right. So
liquefied, which is way denser than air.
Right.
Okay. And then you take the hydrogen and oxygen. And so now take us from there. I got a tank twice as big holding liquid hydrogen and half that size holding liquid oxygen. And you got to keep it really cold because they're liquefied.
Right.
And that's why, if you ever see the launch, you ever see slow-mo rocket launches from Florida,
right.
You see this chunks of ice falling
off the rocket
because Florida is a moist environment and the rocket is cold and it just all the moisture gathers on it. If you do that in the desert, you're not going to have condensation freezing on it.
Right.
Cool.
Okay, so tell me what's happening when you combine, because in the subject of space, you have liquid hydrogen, liquid oxygen. And I just wave my hands and say, yes, it makes water and there's energy.
Yes.
But take me into that.
So a traditional combustion reaction, traditional, not what you're talking about, has a source of fuel that has carbon associated with it. You treat it with oxygen and you produce water and carbon dioxide. What's really neat about
And that would give you energy.
Yeah, and it releases energy. It's exothermic.
That's anything that burns, basically.
Anything that burns.
Anything organic that burns. Yes.
But
And that's why
when
it turns black when it's done, because it lays bare the carbon.
Yes.
Yes. Okay.
Perfect. But when you remove the carbon, you can have a combustion reaction that's much cleaner. And so that's when what you're talking about. So you have hydrogen plus oxygen will give us water.
It'll still be combustion.
Still be combustion.
But that more a cleaner kind, so that the exhaust of that rocket is
water.
water.
There you go.
There you go.
We did it.
That's awesome.
It's very neat.
So do you think in quantum physics, two molecules can see each other before they make contact?
See each other?
In a way that they say, I want to get a little closer to you.
I mean,
With the music.
In my mind, all chemistry is driven around the rearranging of atoms, and that's all driven by electrons, either electron repulsion or attraction. So that's how I think about interactions, is where are the electrons, are they attracted to each other?
What would be cool is if two entangled particles made an entangled molecule.
Wouldn't that be weird?
Whoa,
It would be wild.
So that would be weird. One quantum molecule with its bits separated.
Right.
That'd be so weird.
That would be weird. But they have to be identical. So maybe a hydrogen makes a molecule H2. A lot of oxygen, not nitrogen.
Yep.
We breathe O2 and N2. So they're quantum entangled to make one molecule. That's a sci-fi story right there.
It is.
Wow.
It'd be really weird.
Super cool.
That is very
Okay.
cool.
All right, here we go. This is Alyssa
But you're
Feldhaus.
Kate the Earth Chemist.
Yes.
So that's not a
Not gonna
future book
happen.
coming
No,
at you.
thank you.
All right.
Alyssa Feldhaus says
Okay.
this. Hello, Alyssa from Rocket City, Huntsville.
Alabama.
My daughters, Amelia and Olivia, just love you. My question is, what is the biggest, most impressive, kid-friendly experiment I can do with a 4- and 8-year-old that will keep them interested in science for years to come? We love a good bang and aren't afraid of getting dirty.
Ooh.
Wow.
Okay.
Okay. That's full carte blanche there.
That's a loaded one because 4-year-olds getting with a bang, it makes me nervous. But I think if you have adults involved, you could do the exploding paint can experiment, which is really fun.
That sounds
okay.
So,
What?
You know, hey, with a 4-year-old and an adult,
Wait,
why
the way
not
she
blow
said that.
some paint?
Wait. The way she said it. Yeah, everybody knows the exploding,
exploding
paint can.
paint
Well, I picture it that they could help you set it up and then the adult would actually trigger the reaction. So it's very simple. You just need a paint can, empty, never had paint in it before. Put about an inch of baking soda at the bottom.
Okay.
Take a cup, plastic cup, fill it with vinegar, food coloring if that's your flavor, and then nestle the cup into the baking
Food coloring
soda.
into the vinegar.
Into the vinegar,
Yes.
yep, in the liquid. And then you can put the cup of vinegar into the baking soda. So like nestle it in like a sandcastle.
Right, okay.
Then you're going to put the lid on the paint can, use a mallet to hammer it shut. You want it completely shut, no place for gas to escape. Now get the kids out of there. They can go far away, put their safety goggles on. Then adults also with safety goggles on.
Always safety goggles.
Yeah, shake it up, but keep your head back because what will happen is a neutralization reaction. You'll release carbon dioxide, just like we were talking about earlier with the Mentos and Diet Coke. Yep, exactly.
It's gonna be a
Boom.
psst,
And then
yeah.
the lid flies up. It's really colorful. It's cute.
Now
it
wait a
makes
minute,
a
but
noise.
But why doesn't
you
that
got to
happen?
sit it down afterwards, right? You can't hold that
Yeah,
thing.
you should put it down. Yeah, good point.
Well, how do you know when it's about to blow up?
It happens very fast. So what I do is I go shake, 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 and I slam it down on the table, and then I step back, and then I move on to my next one. And while I'm shaking my second one, the first one goes off.
Wow.
Okay. So why doesn't? So I thought paint can lids were stronger than that. I think paint can lids are tight, especially if you mallet it shut. But apparently not.
Not enough, 'cause
It's no match for CO2.
Exactly, because
Okay.
it's not secured, it's not locked in, and so
It's
you
not
have,
clamped.
It's not clamped, exactly. So if you have all those CO2 molecules coming in, going bop, bop, bop in that lid, it will shoot it straight up in the air. It's very fun.
Wow.
I love that one.
And that happens in seconds.
Yeah.
And the only reason why you put it in a small plastic cup is to keep it separate long enough to hit the lid.
Exactly. And
Because
what's-
otherwise, it will escape. All the expanding gas will escape before you get a chance to mallet it down.
Okay.
Exactly.
So when you nestle it in like that, You keep everything separate. You mellow it down. Now you mix it. Bang.
And you throw it up first, so the liquid's going to go up, and then it all slams down at one time. And so when you shake it, it actually really nicely distributes the vinegar all over. It grabs that baking soda, and then you get the cool acid-base neutralization reaction.
Wow.
All right.
Very fun. But keep your head back. Keep your head back, because you could get hit in the face.
Yeah, see, I'm going to let my kid do that.
How old's your kid?
This is the money maker. I don't care how old the kid is.
It don't matter.
I can't have a paint can blowing up in this. Like, sorry, baby, this is what pays the mortgage. So you shake that can and put it down as quickly as possible.
But you can't overstate the need for goggles
100%.
for all of your experiments.
Yeah. I usually wear goggles, a lab coat, and gloves. It is a little overkill sometimes, but I like to set a good example. It would break my heart if a kid got injured doing something they watched me do.
Gotcha. All right.
Hello, Dr. Tyson and Dr. Bieberdorf and Lord Nice. James from Denmark here. What would you say are the most promising developments in applied chemistry today?
Oh, man.
Do you claim material scientists in your community?
Ooh.
I do, yeah.
Because that's chemistry. It's
It's
all
That is
chemistry.
chemistry.
yeah.
all chemistry.
And it's usually a branch of inorganic chemistry as
Yes,
well. So
okay.
I
Which is
definitely
your
do.
bailiwick.
Yes, that's my
Okay,
favorite.
so
Those
what-
guys are awesome.
So what's
I'm
on the
sorry.
horizon there?
Oh, there's so many different things right now. One of the things I'm really interested in is how we are bonding with AI, and we're kind of trying to use it to help us. And so one thing that I just read
sense.
is that they asked Microsoft AI, what could we do to replace lithium in our lithium-ion batteries?
Good
and
problem.
it took a week, but it came up with an answer. And so now we are
The
able
hamsters
to
in a
use...
hamster wheel. Thank you, AI, for that brilliance.
Exactly.
Okay.
But so now we have an answer. We can use it and go troubleshoot and see if that will work. And so what I'm really interested right now is how those two worlds are kind of merging together
makes
and how we
sense.
can use that to do better research, more effective research. And so that's what's happening right now. And I am really excited about
Well, that's
that.
what AI is best at.
Yeah, so it's AI-guided
looking at-
explorations.
Yes,
Yeah.
yes. Which
All
I
right.
think is
And
fascinating.
looking at molecules is easy for AI. It's like,
Well, it has a lot of information that
Right.
it can
Yeah,
pull
it ingests
together.
everything.
and it can think in terms of, I use the term think, it can think in terms of future combinations that we could never even get to. We would not have time to get
right.
to it because it can calculate them all at once.
Aren't there books that have all the chemical potentials of all reactions?
Oh, are you talking about the CRC?
Yes, CRC.
I have one. It's a huge book. What is that? Oh, what does that stand for? Something
Cambridge Rubber Company. I mean, a Consolidated Rubber Company.
Is that true?
So there are these compilations of all these properties that have been discovered piecemeal and assembled into these volumes.
Okay.
Any scientist, we have a CRC on our shelves. So that whoever that company was, they decided to compile all the information you could ever want in science.
Very
okay?
cool.
You know what I did? I found at auction a CRC from my birth year. So I bought it so that is a slice in time of what we knew about the chemistry, the physics, the bio. It is all science in there, including math. Okay, so here's the point. It's 1,000 pages. It would take me a lifetime to read through it, but AI could ingest it and come up with new
2 minutes.
chemicals. Why couldn't it?
Right. It's the best of both worlds,
Because
right?
you list is the word chemical potential? What is the likelihood that two atoms will come together? What's the
Well, atoms or electrons, because
No,
potential is
your
usually
outer
electrons.
electrons, sure.
Yeah, usually potential when we're talking about that.
yeah
is the difference
activation
between-
potentials or whatever.
Sure, activation
Yeah,
energies.
So energies. So they know it. So the book has it.
Right.
But you're not going to sit there and read thousands of things and come up with a new molecule.
No, let it do it.
But let it do it while you out on the beach sipping a pina colada.
And then you
Exactly.
get a notification on your phone. I found that new you've been looking for.
And then you say, AI, write the paper, publish
It's
it.
like the best grad student you could have. Yeah.
That's so funny.
All right. It's been said, primarily because it's basically true, that there's no understanding of chemistry without physics. And there's no understanding of biology without chemistry. And so I come to the table as a physicist. So when I look at the world, I see the interaction of matter, motion, and energy. The biologist sees the interaction of all life. Yet the chemist is situated between those two. Because to go from inorganic molecules to self-replicating life, there's some complex chemistry involved. In fact, biology is the most complex form of chemistry we know. But it's not only that, it's everything around us. Everything is made of atoms and molecules, and we take it so much for granted that somebody at some point in our past thought about that, what those atoms would do when they were brought together to make a solid object, to make a liquid object, to make rocket fuel, to make those ice packs that you shake and put on your injury. One of them turns cold, the other turns hot. A chemist was in the middle of that. So I don't think we spend enough time paused in reflection of what role chemistry and the chemists who are behind it all have done for civilization. And that's a cosmic perspective. I think that's all the time
That's
we
all
have.
there.
Oh,
That's
Kate,
it.
you got to come back more often.
Thank you for having me. I love this.
Oh my gosh.
It's so fun talking to you.
And your podcast is
Seeking a Scientist.
Seeking a Scientist. And that's with NPR?
It's with NPR, yeah, out of
Wow.
KCR. It's out of Kansas City.
Excellent. And you interview other scientists.
Yes.
And you engage them with their expertise, and you bring your chemistry patina to it.
Perhaps, yes.
Yeah.
I definitely try to bring the science communicator out of the people I interview.
Because not all of them would necessarily be communicators.
Yeah, and,
Yes.
and do kind of like what you and I do, where we feed off each other and kind of fact check a little bit.
Yeah,
and
yeah,
have
fact
that
checking is fun.
Have
Yeah,
the same
yeah.
kind of conversation. And so it's really nice to feature scientists that might not normally get featured. And I love that.
There you go.
Very cool.
Kate Bieberdorf. Well, thanks for stepping through, and congratulations on your new gig at University of Notre Dame. Yeah, the
Go
Fighting
Irish.
Irish.
Fighting Irish.
Yeah, there it is. All right, we'll look to and try to come back some more often.
I will. Thank you so much. I appreciate it. It's always fun talking to you guys.
Oh, yeah.
All right, Chuck. Always good to have you, man.
Always a pleasure.
This has been StarTalk, Cosmic Queries, the Chemist's Edition. Until next time, as always, keep looking up.